So let me recall our goal. Is to understand the irreducible characters of the symmetric groups. Let's write it as description. Description. Usable characters of the symmetric group. So I need some notation. So assume that we have a collection of integers. So this is a collection of, say, positive integers. Positive integers. And let M be their sum. And then to this collection we assign a central function, a character. Let's denote it as follows. A reducible character. Reducible character as follows. Then, the character. This is the character of the induced representation. Suppose we take the group Sn and what is called Young subgroup. And we do simply by the trivial one-dimensional representation. So this representation is the quasi-regular this its space is the space of functions. And the space of functions on the homogeneous space so this is probably the most simple representations which we can fabricate from some subgroups, some natural subgroups of the symmetric groups. So this is my notation for its character. So this is character. This representation. And next, let's slightly generalize this definition. So slight extension. If these numbers are non-negative and some alpha sub I is equal to 0, we simply drop it. So for instance, we define this. You want to define what is this? This is by definition simply and next. Assume more generally that these numbers are integers, not necessarily positive. Then, if some number is negative, then by definition, it's just the zero function. So, for instance, if you want to give a sense to something like this, and this is by definition simply zero. This is the definition. Now I want to define so assume lambda is a Young diagram with n boxes or a partition, say, which is the same. We assume that, as usually, these are non-negative numbers, so k is necessarily greater or equal to the number of non-zero coordinates in lambda. And when we define, I want to define this function, the central function, on the symmetric group is defined as follows. By definition, the sum over permutations in k letters. This is the sign of a permutation tau. And next, we take these induced characters, such a type. So, and with the agreement that if sum of these numbers is zero, it should be dropped. And if sum of these numbers is strictly negative, then the whole function is said to be equal to zero, according to these rules. So, because this is a character, or zero, so this is a central function, and this is a central function too. So this is the key definition. Now I want to state the theorem, which is due to Frobenius. And the result is as follows. So these, the functions of this type, with lambda being a Young diagram with n boxes, are precisely all irreducible characters of a symmetric group. So this is a description we want. It's not simple. Because why? Because the formula itself is not simple. It involves some alternate sum. And next we have some characters which are not very simple object. But nevertheless, this is a result. One may ask how to compute, say, these characters. From the very definition, one can, so this is some remark. What is these characters? How to? So we can assume that all these numbers are positive integers. And how to compute it? It's not very easy. The idea is the same. So assume S is a permutation, and the value this character at this given permutation is computed as follows. We consider all set partitions of the form. We take the set of n natural numbers and represent it as a disjoint union of blocks of subsets. This is a set partition, and then this number is equal to the number of set partitions such that the size of a block number I is equal to this number. And next, our permutation preserves this block. So this is some combinatorial quantity, which is not very easy, but more or less explicit. So we see that the whole formula is rather complicated. A large sum, if say k is large enough, this is a large sum of some complicated characters. But nevertheless, this is an excellent result. So I proceed to the proof. Yeah. First, we start with a simple lemma. Simple. So assume that we have some finite group. And list all its characters, irreducible characters, sorry. All its irreducible and set, introduce this notation, R of G is by definition the Z linear combination of the irreducible characters. So this is something. The characters we know are linearly independent. So this is some subset, some submodel in the space of functions, even central functions on our group. And now assume, so next that chi is a central function. Central function on G. So the claim is as follows. Chi is an irreducible character. So that is chi coincides with some of these characters for some I, if and only if the following three conditions are satisfied. First, these functions belongs to this lattice, this one. So it is a Z-linear combination of characters. If you can verify it, so this is condition 1. Condition 2 says that the scalar product is equal to 1. So let me recall that the scalar product for two functions on a finite group, we define it as follows. The sum of the elements of our group, phi of G, psi of G bar, and this is normalization that we like. So with respect to this scalar product, we impose this condition. And the last condition says that the value at the unity element should be positive. So this is the properties. These properties obviously are satisfied if our function is indeed one of irreducible characters, because we know that obviously it is here. Of course, it's equal to 1 because we know that the irreducible characters are orthonormal, satisfy this condition. They form an orthonormal basis in the space of central functions. And this quantity is the dimension of a representation, and so it must be positive. And so this is trivial. So conversely, assume chi satisfies these properties. Why? It should be irreducible characters. So this is also very easy. So condition 1 means that our function should be of this form with some coefficients which are integers by the very definition. Should be integers. So next we apply condition 2. It says that this scalar product is equal to 1. But what is this? This means that we have this condition. It's equal to 1. Because these functions are orthogonal and each of them has squared its norm is equal to 1. Its squared norm is equal to 1, so we get this condition. But these are integers. So this implies all coefficients are 0 except 1. 1. So we actually have our functions is plus minus some I4. So we conclude that it is plus minus irreducible character. But now we apply this condition and conclude that actually it is exactly an irreducible character. So is it clear, this argument? Well, so this gives us some tool to...
Хи от единицы, наверное, или в последнем третьем пункте хи равно хи.
Третьим пунктом мы проверяем только что значение характера на единичном элементе группы положительное. Почему она должна...
Понял, спасибо.
Размерность. Это размерность представления. Если бы здесь было бы, он был бы минус, здесь знак был бы минус, то да, эта величина была бы отрицательной. So we will apply our idea here, verify these properties for our function. So the first property is evident. Why? So return to our definition. So what we see that our function is a z-linear combination, actually plus minus combination, alternate linear combination of these functions. And these functions are true characters, reducible in general, but they are true characters, so they are contained in our lattice z-linear combinations of irreducible characters. So property 1 is immediate. Now, so we prove how to prove this. So prove this. We have to prove, so we have to compute. And show that it's equal 1. It's not trivial, not. So the idea is follows. Just rewrite the definition of that. We rewrite this. So I recall the notation from the previous lecture. Eta n is the trivial one-dimensional character of a symmetric group S of n. This is just the constant function. Just constant 1. The constant function equal to 1 on the whole group. Okay. And my definition is equivalent to this one. Chi lambda is the same. I will recall what is this. So what this means? So here we have any number satisfying this restriction. So what is this? How to understand? By definition, we have to expand a determinant. What is this? I'm sorry. This is some problem. We need to resolve it. Нет, некоторое время.
А можно пока вопрос задать?
Да, пожалуйста.
А вот мы в самом начале ввели понятие вот этого приводимого характера и от альфа-1, альфа-к. Потом в
Да.
качестве замечания мы сказали, что это такое, что вот это количество разбиений таких, что модуль АИ равняется альфа-И, и S сохраняет АИ.
Да.
А как, собственно, это доказывается, что это именно так?
Это просто определение характера.
Ну, просто как-то вот мы сначала же сказали, что вот этот характер
Это
индуцирован
индуцированный характер.
давлением.
Это индуцированный характер. Так. Он действует. Давайте я потом. Я прошу прощения. Я в конце скажу.
Ну, я тогда после лекции еще раз задам.
Да, напомните, если вас не затруднит, и мы вернемся к этому вопросу. Да. Это требует поправок, это требует некоторого размышления. Мы вернемся к этому. Сейчас я подключу. Это... Надеюсь, что сейчас будет работать. Что еще такое? Ну, вот. Так, что-то временами возникает эта проблема. So how to understand this determinant? By definition, we have to understand it as follows. This is... Теперь тут еще проблема. Что это такое? Ну, хорошо. So this is the sum over all permutations of the symmetry group. The sign of this permutation. And so on. So what means this product? This is the meaning I recall it. It is as follows. This is just induction. Induction from Young subgroups. So if you take some two subgroups, say two symmetric group, which are viewed as subgroup of a bigger symmetric group. And we have just the and phi is a central function on this subgroup, and psi is a central function on this. When we form this function on this subgroup, so if this is G and this is H, then we just write H we may imagine that we identify permutations and the corresponding permutation matrices. So we have permutation matrices size E, Q, Q. So we have G and H. So this is a matrix with zeros in these blocks and some permutation matrix here and here. And this function is obtained in this way. And then the product, I recall the formula, the value of this function on some element G, now I'm sorry, G is an permutation from this group, is given by this formula. The sum of representatives of cosets okay, and we take these quantities until the means that we extend this function from this subgroup by zero outside. So I recall this. So this operation means just induction. And in the same way, we can take some more complicated Young subgroups and take central functions and induce them according to the same formulas. And here again, this is the trivial characters. So we put on each block the trivial characters. And we assume if this number, some number is equal to 0, we just drop it because its contribution, it does not contribute. And if some number is negative, then this expression is said to be equal to 0. We just drop it as a whole. So this is the same as the initial definition. This is the same because this induced characters is exactly this induced product, this product умножения кружочков. So this is the same. I just rewrote this. Okay? If some questions, so please ask. So the question, how to see such a product is it's easy to see. It's easy to see because how to see so the question. Why? So the answer is if you want to take this, it's equal to because this and this is equal to because we can define this as induction from a Young subgroup with three blocks, any number of blocks. Is it clear? Because we can define such a product with any number of blocks. Well, what next? So let me recall some reminder from the previous lecture. So my notation is by definition this one. So I apply the previous notation for, in the particular case of a symmetric group. And by definition, the direct sum of this object with the understanding that this is simply Z. This is a abelian group. This is commutative group, direct sum of a countably many commutative groups, torsion-free commutative groups. And I also need this notation. It's not very good, but nevertheless, this is by definition the tensor product of Z with R. This is simply a space of R linear combinations of reducible characters of a symmetric. So this object is a lattice, a torsion-free abelian group, and this is a vector space of the real numbers of the same dimension. Okay. And likewise, we will write this is direct sum of these vector spaces. And next, I defined a characteristic map defined by this symbol. From this vector space to the algebra of symmetric functions, also over real numbers, actually the nth homogeneous homogeneous component. So this is a map from this vector space to the vector space of symmetric functions, homogeneous of degree of R. It is defined by the following properties. Defined by. If we apply this to this function, then the result is the power sum. Here, rho is a partition or Young diagram with boxes, and I recall that this is the characteristic functions of this conjugacy class, which is indexed by this partition rho. And Z sub rho is some quantity which is assigned to this partition rho. And next I proved we know that characteristic map is preserves multiplication.
Извините, не совсем понимаю запись. Вот пространство функции c от ρ лежит в подпространстве симметрических групп размерности n, или что эта запись означает?
C от ρ – это не пространство функции. C от ρ – это класс сопряженности. Класс сопряженности перестановок с фиксированным, с данным цикловым типом ρ. Может быть, плохо сказал, прошу прощения. В таком виде это понятно, о чем идет речь? Это
Спасибо. Да, спасибо.
перестановок с фиксированной цикловой структурой равной ρ. Это его характеристическая функция, она равна единице на этих перестановках и нулю на всех остальных. So, I proved that our characteristic map preserves multiplication. So, which means that this multiplication corresponds to multiplication of symmetric functions. So this is an isomorphism of algebras. This is very important. Actually, this algebra, which I denoted by this symbol, which is constructed from central functions with multiplication given by this operation, essentially inducing, is the same, actually. It is isomorphic in a very concrete way. It is isomorphic to the algebra of symmetric functions. So we know this, and the correspondence is, by definition, is given by this relation. This class functions, the simplest central functions, corresponds to the power sum symmetric. So we know this. But we also know something more. We know that this also preserves scalar product. We have scalar product on the left and on the right. We have a scalar product on these subspaces, with the central functions. So in particular, with the functions on symmetry group, and we know how to take the scalar product of two functions on the symmetry group by the formula. I recall it is given this one. On the right, we have the scalar product in the algebra of symmetric functions. And we know already that our map preserves also this structure. And finally, I proved that if you take the image of this particular object, identity, constant function 1 on some symmetric group, and it is the same as the H function, which is in the symmetric algebra of symmetric functions. And with all these properties at hand, we can prove our property 2. So I state the following claim. So let's take this particular object, which we are interested in. And the claim is that its image under our characteristic map is the Schur functions. Schur function. Schur. This is very, very important result. So the proof. Why? So I recall that this object is defined as this determinant with respect to this special multiplication. So by definition. On the other hand, we know that Schur symmetric function can be given by a very similar determinant. This is Jacobi-Trudi. The order of this determinant in both cases, the order is k, any number satisfying this restriction in both cases. And the assumptions are the same. Assumptions of a kind that this object is equal to 1 or can be dropped simply if m is equal to 0, and 0 if m is strictly negative. Okay? So if this number, if such a number is equal to 0, and we can simply neglect the corresponding term, corresponds some term of such a type, you can just drop it. This just corresponds to the fact, that HM is said to be equal to 1 if m is 0. And it is understood as 0 is m is negative. So assumptions are exactly the same. And finally, we know that our map moves takes it to, so comparing all these properties, we just get this one. So the important ingredient in this story is the Jacobi-Trudi identity. Okay. Some questions maybe? No. Okay. So, any questions? Is it clear? Well, so we take a corollary. Scalar product is equal to 1 because it is equal to the scalar product, and it's equal to 1. We know this by the very definition, actually, of scalar product in the algebra of symmetric functions. This is equal to 1. So we have verified, right? Condition 2. Well, what next? Now let's verify condition 3. I recall this condition says that this quantity should be strictly positive. How to prove this? The argument is as follows. Let's take rho, this particular partition, which means this 1, 1, 1, and times. And I assume I call that lambda is a unit diagram with n boxes. For this particular partition, the conjugacy class is simply the identity element of our group. Well, and let me recall that Z is equal to n factor. Why? Let me recall that if rho is written in the multiplicative notation, meaning that we have K1 parts equal to 1, K2 parts equal to 2, and so on, then by definition this quantity is the product. Because this product is actually finite, because almost all these numbers are equal to 0. So from this definition, from this general definition, we conclude that we have this equality. The next observation is as follows. So we want to deal with this value, but what is this? This is the same, right? It's as follows: n factorial and the scalar product with this characteristic function. Because this characteristic function is simply the function which is concentrated at the unity element and takes value 1, and this coefficient is introduced because we have to normalize And to take account of this normalization, we multiply by n factorial. But we know that n factorial is this quantity. So we can write this as formally as the scalar product. And this one. But I recall by the very definition that we have this relation. So this is equal. So this is equal to, because the scalar product is preserved. So we can pass to the images. So this is a scalar product of functions on the symmetric group. And now we pass to the corresponding symmetric functions. This is the scalar product in the algebra of the symmetric functions. But we know that this is exactly these functions. I'm sorry, this is a function. The power sum corresponding to this partition. So we conclude that this is equal to the scalar product in the algebra of symmetric functions of the sure symmetric functions and this. And so we have to prove that this is the same as the very definition of what is the power sum symmetric function. This is this object. So I recall this is simply the sum if we realize the symmetric functions as power series. So this is the simplest possible symmetric functions, and we take its nth power, and we have to compute this scalar product. So why? So now the question why this is positive. So introduce my following definition. If lambda is a Young diagram with n boxes, the dimension of Young diagram is by definition the quantity of standard Young tableau of the form lambda. So let me recall what is the standard Young tableau. So if you have some Young diagram, standard Young tableau is a indexation, enumeration of the boxes of the Young diagram by the numbers 1 to n, such that they increase from left to right and from top to bottom. So in particular, we have something like this. This is a standard tableau. and this is not. So this is not stable. Because in this case, in the first case, the number increase, and in this case, they do not increase, they decrease. So I want to prove
А без повторений чисел?
повторений, без повторений. Without. So how to prove? So the claim is as follows. To prove that this quantity is positive, I will show a stronger claim, namely it is equal to this quantity. And how to show this? So we prove. This will follow from the formula. Like this is a symmetric function, homogeneous of degree n. So it can be expanded on sure symmetric functions. And it turns out that the coefficients are these numbers. So we will show this. So simply remark that this implies this relation, because we know that this is an orthonormal basis, a homogeneous component of degree. So taking the scalar product from this relation, we can extract this coefficient by taking the scalar product with this basis function. Okay? So now we want to prove why this happens. So the idea is as follows. This in turn, this follows from Pierre rule. We know it was discussed at one of the seminars that the following a particular case of Pierre rule holds true. If you multiply a sure function by this simplest power sum, what we get? We get the sum over all of the sure functions indexed by all Young diagrams, which can be obtained by adding a box. So if we take some new, this is new, and the all possible lambdas are obtained as follows. We can append one box here, or one box here, or here, or at the very end, but of course not here, because the result is not a Young diagram. So it can be written as follows: this condition, this can be denoted as follows: this, or equivalently, it's just a notation. Okay. But what this means now? So we start. Now we start with the Schur functions which corresponds to the empty Young diagram. This is just the unity. We multiply it, by P1. So we get this one box diagram. So we get from this, we get one box diagram. Next we multiply again by this, and we get the sum. Get the sum of Schur functions, which can be obtained by adding one box. Next, we multiply again. So what we can get, or we can get this Young diagram, and from this, and one more possibility is as follows, and so on. What we get here is the so-called Young graph. Very important concept. Vertices are Young diagrams. Which I also denoted by the same symbol, and its edges are pairs of two vertices of two Young diagrams, such that one diagram can be obtained by adding a box. So these arrows are just the edges of a Young graph. So if you have some Young diagram somewhere, we see that what we denoted by the dimension is exactly the number of paths going in this direction and joining this root vertex with some. So we get the dimension, which is by definition but the standard Young diagrams are essentially the same as sequences such type, which ends at lambda. Okay. But these are paths from the empty diagram to, but this is the same. This is the same by the Pierre rule, rho as the coefficient is in the expansion function. Because the coefficients in the expansion of this function are just produced from these moves, from these paths along the edges of a Young diagram. Is it clear? But what we get, actually, we just proved this formula. The coefficient in this expansion is exactly as the number of paths from this to our Young diagrams. And this is the same as this quantity. So we proved, so we summarize, we have proved property 3. This means by the initial simple lemma that our function is an irreducible character. So what we get? So for any Young diagrams, there corresponds this function which is an irreducible character. Irreducible character. But next, we have, if these are distinct Young diagrams, then these functions are orthogonal as functions on the symmetric Y, because corresponding Schur functions are in the space as elements of algebra of symmetric functions. This implies in particular that these characters are distinct. And the number of Young diagrams equals the number conjugacy classes. Now symmetrical. So we conclude that these functions are just all irreducible characters. So this is the end of the proof of the theorem. So let me summarize what we get. So in particular, we also proved as a corollary of the proof, we get that its quantity, the combinatorial dimension of a Young diagram, is the same as this quantity, which is dimension of the character, which is the dimension of the corresponding irreducible representation. So let me give a little summary. What we already know. we know that the image of this function under the characteristic map is the Schur symmetric function. Next, we know by the very definition of a characteristic map, this is important formula. And third, we know that the scalar product approved this is equal to this remarkable quantity. So you have to take into account these key relations. And from this relation, we can prove the following Frobenius formula. This formula for reducible result is as follows. So that by definition, so that we have two Young diagrams, two partitions, and write this for the value of characters at the conjugacy class this one, indexed by partition rho. So this is this array. This array is the what is called the character table of the symmetric group. So to know the characters is the same as to know the character table. So the formula of Frobenius says that these quantities, the values of the characters at the conjugacy classes, appear as the coefficients in the expansion of the power sum p sub rho on Schur symmetric functions. So these quantities appear in this. So this is truly the great formula for Frobenius. And actually, all that we can obtain about the whole information about the characters, about these quantities, is encoded in this formula. It can be extracted from this formula. This is essentially the unique way, the unique source for the information about characters. So this implies in particular, because we know that the Schur symmetric functions are orthonormal, this implies that this quantity is equal to the scalar product y. The proof is very easy. Proof is I'm sorry, I need a few minutes. It's very easy. Indeed, we have. It's equal to just write it as follows. So this is tautological identity. But this can be written as follows. Number of the cardinality of this set and the scalar product with this characteristic function. This factor appears that this scalar product assumes normalization by n factor. So we add this. But next we observe that this quantity is exactly the same as this one, because this quantity z is the size of a normalizer of any permutation from this class, of this conjugacy class. So this quantity is the same as this one. And next we use the fact that we pass to a characteristic map, and we conclude that this is what we want. So we have proved this formula. Okay. And finally, I want to give some corollary. I'm sorry, I need a few minutes. It says as follows. So assume and capital N is large enough, this one. And we have the following formula, which also can be called Frobenius formula. It's called as follows. Let me write, and then I will explain the notation. This is a monomial. This is the Vandermonde determinant. So what is written here? In order to calculate this quantity, we can do the following. Take the Vandermonde determinant, multiply it by this power sum symmetric functions, but actually polynomial in capital N variables, and extract the coefficient corresponding to this monomial. This is what we want. Why it's true? This is true because of a general principle. If you want to solve it, let me recall the general principle. This follows from general recipe. You want to find the coefficients, the expansions of some symmetric polynomials and variables. We know that such an expansion does exist, but we want here we have to write the length under does not exceed n. So if we want to extract this coefficient, what we have to do, just multiply by the Vandermonde. So multiply both sides by this Vandermonde. So it appears here. And then this is transformed to the alternand. And just keep the leading monomial, which is this one, and take its coefficient. So this is exactly what I do. In the particular case, so we apply this. We apply this to f equal to this function. And from the Frobenius formula, in order to extract the coefficient which corresponds to a given lambda, we impose this restriction. We have to take n large enough in order that this polynomial is not equal to 0. So this is just the application of this general principle. So I'm sorry, I have to stop.